years, and been at the U of A for the last 4, having come more recently out of the government of Alberta, where we have done a lot of work on pretty major transition to the Alberta electricity sector. And I think I can share my screen here. Let me just share one very quick slide, hopefully with everybody. And so this is what is going on in the Alberta electricity sector over the last decade. And so if you're not familiar with what's going on in Alberta, you can see just this rapid transition of coal, which was kind of the backbone of our system up until 2 or 3 years ago, and a rapid rise in natural gas and renewables sort of increasing. But this is kind of where obviously there's lots of growth that's expected with thousands of megawatts, both of solar and wind in the queue. And so it's a super interesting time to be looking at the electricity sector in general, but then also probably this pretty significant increasing role that renewables have to play. So with that, I'm pretty excited to be here to listen to what else is going on in the rest of the country and to learn about some of the research that's going on with wind integration more broadly. So I think for those of you that were here on Monday, same sort of format, we'll have relatively brief presentations. And then I think the way I would like to do it is if there's sort of one burning question that someone might have as a clarification after a presentation, we can maybe field a follow-up question, and otherwise we can generally sort of hold our questions for a broader discussion at the end of the event. So with that, I think that hopefully gives us a sense of kind of what to expect for this morning or this afternoon, depending on where you are in the country. And I'd like to hand it over briefly to Rup Caraveau from University of Windsor, if he's here, to just give a quick intro to. I am here, Tim. I'll let you take over for a second then.
Despite their best efforts, I broke in, I made it. Yeah, well, look at all the people here. Holy smokes, this is amazing. So yeah, this is a welcome from the steering committee, and I do have slides, mandated slides. They try to control what I say. So do I share those, or will you guys put them up, Marianne?
If it's easier, I can put them up.
Please, if you don't mind.
Sure. Can I share, Jeremy? It's like.
Yeah, you should be able to share it just fine.
Okay. Can everybody see the presentation?
I want to see my screen.
Not yet.
I cannot.
There it is. Awesome.
Okay.
That's the third slide. Can we go back? I'm seeing the third. There we go. Awesome. Thanks, Marianne. That's dynamite. So yeah, in all seriousness, I'm really happy to be here. This is terrific, and I'm thrilled that to be part of this steering committee, which has sort of put me on the inside to see this kind of come up from the beginning, which is really neat. And this has really been brought because I think we've been missing for the last few years a really good Canadian forum for research collaboration. So we've got universities, independent research organizations, government, and industry here. And this network is really keen to learn about all stages of research progression. So from the most fundamental to the very applied, and there's a firm belief that the collaboration is sort of inevitable here, because we've got really interesting people doing neat things, and the collaboration is necessary as well. It's born out of necessity, because to sort of push wind forward in its great state of maturity as it is now is a daunting task. Next slide, please. So right now, the modest, but I think really effective goals have been to have at least one meeting a year, and members with intersecting areas of interest engage in, we were trying to get people to build teams so we can pursue funding in the most capable way possible. The steering committee has members that include Ryan Kilpatrick from CanMed Energy at Enercan, myself, and my wiser colleague, Lindsay Miller from the University of Windsor, and Phil McKay from the Canadian Renewable Energy Association, Charles Gaudreau from Nergica, and of course, Scott at WeCan, and of course, Marianne at WeCan. Next slide, please. So this is our second annual meeting, and it's a series of webinars with very short, punchy presentations, followed by a brief discussion, and I'll try to keep us on track by not prattling on too long. So yesterday was an outstanding day of wind turbine aerodynamics. Today we're talking grid integration and curriculum development. Tomorrow, or next day, sorry, day 3 will be cold climate forecasting. That's coming up on Friday. And then following that on the Monday, we'll have offshore wind and social environmental integration. And finally, on the Wednesday, April 13th, we'll have asset management. So all this is being recorded, which is fantastic for archive, and people can take it away with them. So that said, welcome, and let's have some fun.
Great, thanks so much. Appreciate the introduction, and I really appreciate the fact that these are being put together. I remember it wasn't that long ago, doing academic research in renewable energy. There was you could count everybody on one hand. You knew the community pretty well, and so it's nice to see some new faces, and also just nice to see how big the network's growing. So this is a great initiative, and I really appreciate that's it's been put together by WeCan and the rest of the steering committee. So without further ado, then let's hand it over to our first speaker from Nergica, Dominique Bolduc. If you want to take it over, I don't know if you have control of the screen or not, but
yeah, we'll take it.
Perfect. All right, take it away. If anyone has any questions, feel free to put them in the chat. That's probably the easiest way to follow up with questions.
So I'll just share my screen. Presentation. Good, so everybody can see my screen. Go. So my name is Dominique Bolduc. I'm an expert analyst at Nergica. I'm also the leader of the Nergica for contribution to IEC Wind Task 19. So for people who don't know what is IEC Task 19, actually it's the international committee that has the purpose to expand and coordinate, facilitate international research on wind as a distributed energy. So this year, the main benefit from Canada that we consider to be important was to be able to draw the attention to the challenge inherent to distributed wind and off-grid community. So we can see that every country has their own challenge, and that Canada is not an exception at all. So for the Canadian context, we can see actually that there's a lot of lack of official public data about distributed wind. So, and partially, if we compare to NREL in the US, we evaluate every year the progress of distributed wind in an annual report. We can see that not much data can be found on our capacity as a distributed wind country. So also we can see that energy as being a provincial competence, we can see a lot of difference in policies to integrate distributed wind. Like, for example, you can see a variation of 50 kilowatt to 1 megawatt of net metering program for, if compared to Quebec and Nova Scotia, for example. Moreover, we can notice that some market that distributed wind is not able to compete with the cost of energy of the utility grid, especially for fixed tariff programs. So we can see that Ontario and Alberta have policies for higher distributed wind capacity that helps developers to have a more dynamic presence in the distributed wind presence. So this leads us to realize that our best market for distributed wind is actually isolated community, especially because of their heavy diesel reliance and high costs associated with it. However, this market comes with their barriers like low data availability, logistic constraints to install wind turbine, limited wind energy deployment, harsh environment, and weak telecommunication network. However, we can see that harsh environment means, especially in northern community, low temperature, which means higher density, and also very high wind. So a very good energy resources for those communities. Other barrier that has been focused in the task 19 is the barrier with turbine provider. You can see a lot of turbine providers struggles financially. So some went bankrupt in the last few years. Some we don't necessarily know if they're still in business. So, and there's also a lack of validation on the performance of some manufacturers. Some also offer cold climate version, but the remaining one that are still in business actually don't offer that much cold climate version for their turbine. This leads some community to go for bigger players like Enercon technology that have their pros and cons, and that are not necessarily a good fit for this community because of the size of the turbine that they offer. So our main contribution for the last year was to apply the PNNL distributed wind valuation framework to a Canadian context. This framework established quantifiable and qualitative metrics to demonstrate the value of including wind energy for all parties, like the community, the developers, and the utility. Also, Energica's experience in cold climate in the contribution in task 19 enabled to validate some security aspect of implementing wind turbine close to northern community regarding, as an example, ice probability. Regarding the barriers that we identified before, Energica was also mandated by Enercan to identify potential technology providers for northern communities and to identify the barrier that can slow down the integration of wind turbine in these communities. Also, we can note the Professor Wood, that is part of the Canadian delegation, Task 41. Professor Wood is actually involved in, excuse me, I just switch my, work to improve the simplified load methodology for the upcoming version of the small wind standard, small wind turbine standard, and also to improve the modeling of tail fin on small wind turbine. So that's what was our contribution for this year in task 41. So if you have any questions, please.
Hey, Tim, do you want questions right now, or do you want to save them to the end?
I was just going to say, if right at the beginning there, if we've got one sort of burning question, we can you can have at it there, Tom, and otherwise we'll save the broader discussion for the end. But if there's one,
yeah,
you want
it might be too much of a loaded question. I'm just curious about the PNNL valuation and what kind of feeds into that. So it's probably a broader discussion.
That sounds like a long answer. Can you give a short answer there, Dominic? And if not, then we will hold it for
I'm not
afterwards.
involved in this validation, but from what I understand is that this framework identify metrics depending on what type of installation is made, if it's behind the meter, in front of the meter, and depending on the type of installation, we identify different metrics. So we collect information on the project, and after that, the metrics can tell the valuation of each aspect for different parties in the project.
Okay. All right. Thanks.
Perfect. Thanks, Dominic. And we'll be around for the broader discussion if anything else, anyone else has any further questions. So. Perfect. Thanks so much. Our next speaker then is Abby Morneau. Is Abby here with us?
I didn't notice Abby, so I think I will present on her behalf.
Okay.
Okay.
We can handle that. Okay. All right.
And again, will you guys share that, or do I share it? I have it.
Whatever's easier. I have it too.
Okay, if it's easier for you, Marianne, I'm happy if you do that.
Okay. What I want. There. Can you see it now?
I can. Fantastic. Thank you. So thank you very much. Excited to be here to present this. And I'm presenting this on behalf of my colleagues at the Turbulence and Energy Lab and the Great Institute, Dr. David Ting and Abby Morneau at OGVG, Aaron Korstein, Nikki Bennett, and of course, a good friend known to many of us, JJ Davis. Next slide, please. So a little bit about the demand side of this challenge that we're dealing with turbines and tomatoes. Leamington Kingsville in southwestern Ontario, and it's home to over 3,000 acres of greenhouse agriculture. It's the greatest concentration in North America of greenhouse agriculture. And so it's growing as a sector. It's doubling in 5 years. The power load will actually quintuple in the next 5 years. So it's a very thermally and electrically energy intensive sector. And a huge proportion of the electricity and heat comes from natural gas. Next slide, please. So we've been doing a lot of work in this sector, trying to provide distributed energy resource solutions that involve everything from cogen to solar thermal, batteries, et cetera, in microgrid architectures to sort of help the sector expand while they wait on central grid expansion. And even as central grid expansion is outpaced by demand, more and more DERs are needed to sort of take care of that. This slide here shows you just sort of an idea what the pattern looks like for the thermal demand expressed in power here in megawatt hours per acre. This is a sort of characterization of 5 different greenhouse types. This is real data from these 5 real greenhouses that have the 3 main crops, which are peppers, cucumbers, and tomatoes. And some of them are lit, some of them are not lit. They're all put together here as sort of an average. Next slide, please. This is the electricity side of the demand. And these, now we see the 5 greenhouses represented individually. And what you will notice right away is that there is a staggering difference in the electrical demand as soon as you put grow lights on in your facility. Up to like 45-fold increases in your demand can be expected. You see the same seasonality, that the winter months require more energy. We saw it on the thermal side, and on the electrical side, we don't use the lights as much in the summertime. Next slide, please. So therein lies our challenge. It's an economically fantastic industry for the country, and in Ontario specifically, it's a $3 billion gate. So economically restraining it because of a lack of heat and power is a bad thing. Not to mention there's an environmental footprint with the current power solution, which is largely natural gas. So fortunately, we also have a large concentration of wind energy in southwestern Ontario. And a lot of these guys are transmission only. In fact, just about all of them are transmission only, and they're connected on these 20-year power purchase agreements, which will be rolling to an end at some point in the coming years. In fact, 5 or 6 years in some cases. So wind farm owners are actually thinking about ways to sell their power to other customers potentially on the other side of their first PPA. Next slide, please. So over some really bad pub food, JJ and I started talking about what possibilities could be for something like this. And we were looking at some of his farms, which currently only sell to the province as per their contract demands. But that could be altered, and we could potentially send some of the electricity from the farm, from his substation, over to a battery to increase flexibility, and then directly to power lights at a commercial greenhouse. Some of that power can also be diverted to run an electrolyzer that's juiced up with water from nearby Lake Erie. And that is going to provide clean electricity and clean heat for this greenhouse sector. So it enables immediate expansion opportunities. It also provides another avenue for revenue for wind farm. It's a novel wind farm configuration for Ontario. New things to do on the other side of the first PPA, and it really cleans up the environmental footprint of the growing greenhouse sector. Last slide, please. So right now we're in the throes of putting a team together that includes Enbridge, Kruger Energy, Ontario Greenhouse Vegetable Growers, and of course the University of Windsor. And we are building up a parametric economic model that will allow us to generate transparent business cases for this type of solution so that we can move the needle with the policy changes that are required to make this happen from a regulatory point of view. So very excited about the project and excited to talk about it more at an appropriate time. Thank you.
Hey, Roop, it's Tom. Why don't you reach out to me and we'll do a deep dive on this with our group. It looks like you definitely moved the needle forward on this, so I want to hear more about this.
Thanks, Tom. Yeah, no, things are happening fast and furious, at least in this province. So really happy to connect. Thank you for that.
That's great. It's super interesting to see the transition from Ontario. Obviously got a bit of a bad press over the years from maybe some of the high prices in wind to suddenly this world where wind is going to be coming off PPA and be incredibly cheap. So it's a super interesting time to sort of to watch that unfold. And I think we're starting to see the early years of that as feed-in tariffs start to roll over in Europe as well. So that's great. I'm really thanks for that. We'll now move on to our next speaker, Eldrick from WeCan. If you want to take it over from here.
Thanks, Tim. Just the usual tech confirmation scan. I need one person to confirm. Can you see me? Can you hear me? Can you see the presentation?
Yeah, you're good.
Perfect. So my name is Eldridge Rebello. I am with the Wind Energy Institute, WeCan, same as Marianne. My presentation here today is about work that we did with something called the Utility Forum. This is something that was funded through Natural Resources Canada, and it has representation from all 10 provincial system operators. So this presentation focuses on results from the first task, which is, it has a long title, but you can condense it down to, just give me 1 second, the transition hasn't worked here, which is you can condense the title down to the first bullet here, which is renewable generators can do a lot more than simply providing cheap energy. So this slide is the what and why of what's in the presentation. There are a lot of results. I will not go into too much detail there. I'd rather like to focus on the broader picture here. There's a link to the project report at the bottom. Don't worry if you can't click it. I have a QR code at the end. So hopefully you can grab your smartphone or maybe turn your tablet around and scan the QR code that way. Now back to the subject here. The simple fact is that renewable generators, so things like wind and solar, they can do a lot more than simply provide cheap energy. One of the most frequent criticisms about these sources of energy is that, well, the wind's not always blowing, the sun's not always shining, and there's a burden placed on the grid. The reality is that these generators can address some of those issues themselves. One of the chief selling points of this work is that it's not a simulation. So what we did here was a field demonstration with actual turbines in the ground connected to a functional power grid. Now, why is this important? It's because of the simple fact that if you or somebody else were to repeat this with similar technology, it's fair to claim that you can expect similar results. So the main implication here is that this analysis accounts for real world conditions and real world limitations. So it's not an ideal world. It's not the ideal world of a simulation. Who was involved here? It was three parties, Nova Scotia Power, who are the utility and the wind farm owner. And I must emphasize that this was a big help. It was a big help, the fact that Nova Scotia Power were both the utility and the owner of that wind farm. It just made coordinating things a lot easier. Second, of course, was Enercon Canada. The wind farm was the Nutby Mountain Wind Farm in central Nova Scotia, and it has 22 wind turbines. The total power is roughly 50.6, I believe, megawatts. And of course, we were involved with project administration and data analysis and reporting. The one thing I must mention here is nothing I'm about to present is either new or novel or spectacular or anything along those lines. The real value of this is that this is an independent analysis. So think of it as taking the 0 to 100 times for a bunch of cars. Would you trust the numbers from BMW, Mercedes, Porsche, Tesla, or would you rather have somebody independently verify those numbers and confirm what the manufacturers are telling you? Just to be clear, I'm not saying that Enercon or anybody else are wrong. I'm just saying that there's no conflict of interest here. So we have no conflict of interest in telling you what the real story is. So this is where this wind farm was in Nova Scotia. It's in the center. I won't dwell too long on this. I'll just move on to what was tested. So we tested a couple of things. First was fast frequency response. So what is this and why is it important? What this does is you can see on the plot on the left here, that's the red line is a plot of frequency versus time. So this is grid frequency, and if grid frequency falls by the amount shown here, that's usually a sign that something bad has happened to the grid. So there's a transmission line that's failed, a tree has fallen on it, or a generator has gone offline for some of the other reason. If this is not arrested or if this is not solved quickly, it can lead to cascading problems. So this is something that's very important, and it's very important that all generators contribute to this in some way or the other. Typically, older machines, so say synchronous machines, this is an inherent property of how they work. What's unique here is that wind turbines can achieve the same thing. So they can provide a fast frequency response with the added benefit that because there are power electronics involved, the response is tunable. So on the left here is an example of a frequency signal that was injected into the turbine control system. Now bear in mind here, when I say that this frequency signal was injected, we tricked the wind farm into thinking that there was a grid event. What really happened was there was no grid event, of course, but throughout this response, the farm remained connected to the Nova Scotia grid. Now, I won't dwell too much on the background here of what's presented on the right. You can find more information in the report. I'll instead move on to what exactly we were looking for here. So what fast frequency response does is it injects active power quickly to counter a fall in frequency. So the way we set this up was once frequency dropped below a threshold, the entire wind farm would inject 10% additional active power. So that's 10% of the rated power. So 10% of 50 is approximately 5 megawatts. It would try its best to maintain this for 10 seconds. And Enercon's claim was that you can reach 63% of the boost value in 1 second. So to summarize here what's happening, grid frequency falls, the wind farm detects it. To counter the frequency fall, it starts injecting active power. The ultimate source of that active power is the wind turbine rotor. So that causes the rotors to slow down. The results here, long story short, it's pretty close to what we expected. On the left and the right, you can see that the expected values were 1 second on the left and 2 seconds on the right. The calculated values were just 200 milliseconds longer. That's pretty easy to explain with measurement delays and control system delays and so on. But this worked as advertised. The one bar that's in red, that's where we had a communication failure. But as I said earlier, we don't have a conflict of interest. So I can put this on the graph and tell you exactly what went wrong there. That's in red because the response did not trigger, and it didn't trigger because there was a communication failure. The magnitude that we expected, so the left plot here was was at least 5 megawatts. You can see that in almost every case, it's more than that, with the two exceptions in red. So in the lower one, there wasn't enough wind, and in the upper one, it was a communication failure. There is a chart on the right that shows the response drop. The gist of this is if you slow down the turbine rotor, it does need time to accelerate back up to operating speed. That causes a dip in active power. This is an entirely separate discussion. How much should it fall and how long should it take to recover? I won't get into that discussion here, but there's more information in the project report. The second test here, so this is the second of 3, was something called droop frequency response. This has the same general idea as the previous one, except that it's slower. So where fast frequency response is working in a couple of seconds, this is working on tens of seconds. But the general idea is the same. If frequency falls, the expectation is inject more active power, and the other way around also. So if frequency rises, reduce active power. You can see there's a bit of a challenge here, given that most wind turbines generally track maximum power. So if they're already extracting the maximum power available in the wind, how do you inject more power than what's available? In the previous example, so with fast frequency response, you slow down the rotor. That's not what's done here. You're talking about a power response of sometimes minutes. Now you can't slow down wind turbine rotors for several minutes. So the obvious solution is to curtail them and to curtail the wind farm and to operate at a lower than maximum power. That's not good if you're aiming for things like renewable energy credits. So for obvious reasons, we did not test that half of the response. We tested the other half. So what happens if frequency increases? How well does the power curtailment work? As you might expect, the results are the results are on the next slide. This is a bit more information about how this works. So like the previous case, the red curve here is the injected frequency, and Enercon provide you an equation to calculate the power curtailment. So that's shown with the green crosses. As before, it largely worked as expected. So instead of producing a graph that said yes for 37 repeats of the same test, what I've put here is average error. So this is the kilowatt error between the expected power curtailment value and what was actually achieved. You can see that it's generally pretty good. The lower part of the graph is where wind speeds were variable. So as with anything connected to a wind turbine, it depends on the wind speed. That's the most important reason why the error was slightly higher towards the bottom. The last set of results I've got here is AGC. So this is essentially curtailing the wind farm's output to follow a certain signal. Now, what is AGC? It stands for Automatic Generation Control, and it is a means of balancing demand and supply on the time scale of seconds. So when you turn your lights on, that power has got to come from somewhere. If there are 1,000 people turning their lights on, what you get is AGC. So this is simply balancing supply and demand. And the long story short here is it worked pretty well. The one slight caveat is we don't have a lot of data here. It's about 45 minutes in total. Now to put a number to how well, it's actually very well. On the bottom here, I've got a plot of performance scores, which is an attempt to put a number to the term how well did it work. And this is from the California system regulator. You can see that wind and solar tend to do pretty well. Their performance scores are usually in the 90s. The performance score for that limited chunk of data we have here is in the high 80s to high 90s. So that's pretty good. That's essentially saying it was bang on. So there was a lot of information I just hurled at you, but the gist of all of this, or the one thing I want you to remember, is that wind farms, especially modern ones, are capable of doing a lot more than simply providing energy. These services that they are capable of providing, they work pretty much as advertised. This work is an attempt at quantifying and critically evaluating how well that can be done. There's more information, of course, in the project report, and I'll stop here for questions.
I'd like to jump in here too and acknowledge that this project was funded by NRCan. The utility forum is NRCan's utility forum, and they funded this demonstration project. So we'd like to thank them for that, their help with this work.
It was an epic lift. Thanks, Marianne.
Tom, I'm going to pause for your question here.
Well, honestly, Tim, I've been going a bit back and forth with Scott on whether I should ask it or not. But I one of the things I had kind of started out a long time ago when we were kind of coming up with these concepts was it feels like we're going to have to march across the country, every single province. We're going to prove it to every single utility because, well, hey, just because we did it in Nova Scotia doesn't mean it's going to translate well into Saskatchewan, which is fair on some levels and not necessarily on others. One of the things that we also did through this, I say we, it was a lot of people here is looking at grid codes and I'm thinking out loud, how do we get these results and translate those into actual grid code lines like we're seeing in Nova Scotia? The TSIR was modified to contemplate provision of these various services, including reactive power, which we didn't do in this test, but what does that mean line by line within grid codes? Where do they need to be updated? Where do they need to change? And can we take the results of this one test and maybe some of the other PERD work and put that in? It's more just kind of what's going through my mind right now. It's not necessarily a question, but something definitely to think about. Tim, maybe following up with you to get your thoughts on that.
I'm not sure if there was a question in there.
No, there wasn't. It was just more brain dump at this point.
I don't know if Eldridge, if you have any response to that at all. Thanks to that, Tom. I do appreciate the idea of having to repeat this. Every grid likes to think it's unique, but
my only response would be that I agree with that. There's not a lot much more to add there. It's important that we do work like this, mostly because this can serve as an input to other people's simulations. So simulations are based on something from the real world. I think this is just step one of many steps.
Yeah, otherwise, I guess we end up living in a world like Tim's epic background there.
That's just
kudos, by the way, Tim.
Good. Well, I'll steal the microphone back from Tom here then. And Eldridge, thanks very much. Super interesting work, and it's great to see that being presented and doing the work of verifying as an independent verification, and that the results were so positive. So that's fascinating work. Seeing renewables move beyond sort of just an energy only product is very interesting times. We've come a long way. Okay, well, thanks for that. Then, if anyone has any other questions, as I said, we'll hold them to the discussion at the end. But let's pass the microphone and camera over to Sophia Guzman from Mohawk College.
Oh, hi! Can everyone see my screen?
Yeah.
Yeah. Good afternoon, everyone. My name is Sophia Guzman. I'm an energy specialist at Mohawk College, and I'm really happy to be here with you today. Today, I'm going to talk about frequency regulation support with fast energy storage systems. My slides are not moving. Give me 1 second. Okay. So the work I'm going to present today was part of my PhD program at the University of Waterloo. and was done in collaboration with Professor Claudio Cañizares and Kankar Bhattacharya, Dr. Mariano Arriaga at Moja College, Daniel Sum at the Independent Electricity System Operator of Ontario, and Professor John Simpson Pargo at the University of Toronto. I would like to thank the NSERC Energy Storage Network program for funding this research, and also to the ISO for providing the data to make this research as practical as possible. This is the outline of my presentation. I will start with the motivation of this work and its objectives. Frequency regulation model of pool power systems with energy storage will be presented, followed by regulation signal design and fast frequency control with energy storage. And conclusions and next steps are going to be presented at the end. High penetration of renewable energy sources and their associated intermittency are causing frequency regulation challenges in bulk power systems, which can be addressed by using fast response energy storage systems. Several policies are being modified and new services are being created to facilitate the provision of regulation services by energy storage systems. Thus, there is a need to develop models of bulk power systems with energy storage suitable for frequency regulation studies. Currently, in Ontario, there are 2 regulation signals which are generated independent from each other, causing the resources to work in an uncoordinated manner. Hence, an optimized strategy to split the regulation signal can improve the frequency regulation performance. The state of charge of energy storage facilities and the communication delays in the signal transmission impact the frequency regulation performance, and thus they should be modeled to obtain realistic results. The objectives of this work are, first, to develop a model of a large interconnected power system operating under normal conditions. The model, suitable for frequency regulation studies, should be able to run in short periods of time, and it should include empirically based state of charge models for flywheel and battery energy storage systems and communication delays to analyze their impact on the frequency regulation performance. The second objective is to propose a novel H2 filter design procedure to optimally split the frequency regulation signal into a fast component sent to the energy storage facilities and a slow component sent to traditional generators to minimize the area controller variations. The filter is integrated into a validated frequency regulation model to form an integrated model. The third objective is to demonstrate the impact of fast response energy storage systems on the frequency regulation process by applying the proposed integrated model to the Ontario power system. We develop a model for frequency regulation studies of a large interconnected power system that includes all the main stages in the frequency regulation process, communication delays in the signal transmission, and empirically based state of charge models for flywheel and battery energy storage systems. Stage 1 of the model calculates the area control error-based signal that is going to be sent to traditional generators and energy storage facilities. Stage 2 is the area control error filtering block, which purpose is to get rid of fast signal changes, since the traditional generators are not able to react to this. Stage 3 processes the area control error filter signal and delivers the scheduled regulation signal sent to traditional generators contracted for regulation model in stage 4. Stage 7 is the system model and represents the primary frequency response of the elements in the system and the power in the tie lines. Stage 5 calculates the regulation signal to be sent to the energy storage facilities, which is in essence an scaled version of the area control error signal received from stage 1 and accounts for the state of charge of the facilities. Stage 6 includes a model of the battery and flywheel facilities, as well as their state of charge management model. Stages 1 to 4 and stage 7 constitute the bulk power system model, and stages 5 and 6 constitute the energy storage model. The model in general was validated using 1 year of real data from the Ontario power system, a detailed model of the Eastern interconnection, and real data coming from a 2 megawatt flywheel and a 4 megawatt battery energy storage system provided by the Independent Electricity System Operator of Ontario. The design approach used here is to filter the frequency regulation signal by introducing an slow variant component or reg A. Give me 1 second. Okay. By producing a slow variant component or reg A to be sent to traditional generators, while the remaining fast component, or REG-D, is going to be sent to the energy storage system. The design of the filter is formulated as an optimal control design problem, with the configuration of the design problem presented in this figure. It consists of a filter to be designed and a generalized plan constructed using the simplified nonlinear version of the base case model and introducing appropriate disturbance inputs W and error output Z to be kept small. The signals Y1 and Y2 coming out of the generalized plan correspond to the plant measurement outputs provided to the controller, and the signals U1 and U2 are the outputs of the filter. These blocks can be represented by this transfer matrix relationship. And the objective of the proposed control problem is to design a filter FZ such that the H2 norm of the closed loop transfer function from the disturbances W to on the control variable Z is minimal in the H2 sense. In order to develop the H2 filter, a simplified linear version of the base case model was used in the design phase. The various filters FW and FZ are associated to each element in W and Z, specify the magnitude of the disturbance and error signals, and allow to shape the closed loop response. The filters FW are selected as constant gains here, based on the largest change observed in the real data provided by the ISO for each input. The filters FZ1 and FZ4 are selected as constant gains, and FZ2 and FZ3 include a constant gain multiplying a high pass and low pass filter, which can be determined based on the analysis of the discrete Fourier transform of the measured area control error signal. Furthermore, all the constant gains present in the filters FZ can be determined using a recurrent process, which includes a genetic algorithm. The integrated model presented in this figure corresponds to the base case model presented before, with some modifications and the addition of the proposed H2 filter. The modifications presented in green include the substitution of the area control error filtering block and the automatic generation control block by the designed filter, the addition of a 90 wind-up strategy, and a proposed set point calculation replacing a previous set point calculation block. The proposed H2 filter sends the Reg-A and Reg-D signals considering the state of charge of fast resources and capacity limits of the energy storage systems and traditional generators, and depends on the conditions of the system working in a coordinated manner. The anti-wind-up strategy acts by avoiding saturation of the filter, and the proposed set point calculation enforces an idling mode in the energy storage facilities and allows regulation capacity from the flywheel and battery energy storage systems to be significant as compared to the traditional generators' regulation capacity. Due to the limited time, I'm only going to present 2 case studies. More can be found in the publications shown at the end of this presentation. The case studies, these 2 case studies focus on demonstrating the effect of communication delays and limited regulation capacity in the frequency regulation process. This first case aims to demonstrate the effect of communication delays in the regulation process. The signal presented here correspond to the demand, the total generation, the output of the traditional generators contracted for regulation, as well as the output of the flywheel and battery contracted also for regulation, their state of charge, the frequency, power in the interconnection, and the area control error signal. The sum schedule capacity is 100 megawatts coming from traditional generators and 50 megawatts from energy storage systems. When communication delays are ignored, the area control error is reduced. However, ignoring communication delays in real system can potentially lead to errors in determining the regulation capacity needed and the impact on regulation resources in reducing the area control error. The proposed filter takes into account communication delays in the design process and in the system to send appropriate frequency regulation signals. We can note that the integrated model, which is the signal in blue in both cases, yields a small error, and that in both cases, the reduction in the area control error is due to the absence of communication delays. To analyze the impact of the limited regulation capacity, the cases with unlimited and limited capacity with communication delays were considered. We can note that the integrated model yields better result in both cases, as we can see here in the table. When the unlimited regulation capacity is considered in the integrated model, the area control error reduces significantly, And more importantly, the system stays stable. The base case model, which is the signal in red here, becomes unstable when unlimited capacity is considered because the Reg A and Reg D signals are generated independent from each other, resulting in an uncoordinated operation of the frequency regulation resources. These are the conclusions of this work. The smaller the communication delay, the smaller the area control error. And reducing the delay has a similar effect on the area control error as increasing the frequency regulation capacity. Ignoring the state of charge of the energy storage facilities in the regulation process yielded unrealistic area control error reductions. A combination of reduced communication delays and increased fast frequency regulation capacity can realistically improve the frequency regulation performance and reduce the regulation services cost, which for 2021 were more than $29 million for the Independent Electricity System Operator of Ontario. The proposed optimal coordinated control, which take advantage of the high ramp rates of the energy storage system, is required to properly integrate them in the system while improving the regulation performance, avoiding system instability, and reducing the area control error. Analyzing the maximum regulation requirement using the integrated model allows for sizing of the regulation resources. And from the ISO's perspective, the participation of energy storage systems and the proposed H2 filtering strategy can improve the frequency regulation performance and reduce the overall capacity requirement. Based on the work presented here, the following issues may be undertaken for future research. Use the proposed energy storage model to examine how changes in the operational bands of the state of charge affect the frequency regulation performance. Investigate the viability of distributed frequency regulation from fast response energy storage systems to address the issue of communication delays in centrally generated frequency regulation signals. And model and study the impact of synthetic inertia from batteries and flywheels on the frequency regulation for large interconnected power systems. This is all on my side. Here you can find the 2 journal papers that came out of this work. And here's my contact information in case you have some questions or you want to reach out to me. I also have posted here 2 links for the Energy and Power Innovation Center at Mohawk College. If you want to check out the work we do really cool stuff with industry and some utilities, but we're really interested to work with anyone with like very cool idea. So if you want to work with us, just take a look at it and reach out to us. Thank you.
Great, thanks. Thanks very much. Has anyone got any quick follow-up questions? I see Tom's already got his. Is there anyone besides Tom that has a question?
Sure.
Tom's question is about the data itself. Did the data come from an actual operating energy storage system, or I think that?
Yeah. So we use 1 year of real data from the Ontario Power System for all the signals to validate all the blocks in the model. And to validate the model of the storage facilities for the flywheel and batteries, we use actual data of a real of a flywheel and a battery providing frequency regulation for the Ontario Power System.
Perfect. Thanks for that clarification. Great. There's nothing else that's burning then as follow-up questions. We'll hopefully come back to them.
This is Mariano from Mohawk College. More than a question, a comment, because of the work that Eldridge was presenting and this work, I think, and the question about the standards from a policy perspective, maybe there's Eldridge, maybe there's a conversation to be had about how potentially to link this work.
I think so. Maybe, yeah, that sounds like a good idea.
Perfect.
Perfect. Yeah, it definitely seems natural connection there. Great. Thanks so much, Sophia. So then we'll hand it on to our next presenter from the University of Alberta. So Taylor Polinchuk, I'll hand it over to you to take it from here.
Thanks. Just give me a second. All right. Hopefully, are you guys able to see my screen there?
Yes, we can.
Perfect. All right. So yeah, I'm Taylor Polinchuk, and I'm just going to share a little bit of our research that we've been working on, focusing primarily on the optimal geographic concentration of Alberta's wind energy fleet. And this is done in collaboration with the Cabri Center at the University of Alberta. So I'm going to start kind of starting off at the basics, talking about why wind power is relevant in Alberta, why it's worth researching. And I'm going to introduce a wind discount and what that is, what it looks like in Alberta, and why that matters. And then I'm going to talk a little bit about how geographic distribution affects the wind discount and what it looks like in Alberta, and how that leads us into our research, what we're trying to do, how we're trying to model it and analyze a potential distribution that could solve some of these problems. So to start off, why do we need to research wind power in Alberta? So in 2020, 9.6% of Alberta's electricity demand was met by wind power, with about 1,800 megawatts of installed capacity. And that resulted in a capacity factor for wind power of about 37% for that year. So wind power is doing fairly well in Alberta. The installed capacity is third in the country. But when you compare that to the electricity demand that was met by combustible fuels, which was about 76%, you can see that there's a lot of room for growth, especially as we move towards a greener economy and a net zero future. So we've already started to see some of this growth. In 2021, there was over 350 megawatts of energy that came online in Alberta. And at the end of the year, there was over 1,400 megawatts of wind energy under construction in the province. And I really like this chart that you can see here on the side. This is provided by the Canadian Renewable Energy Association. And it shows with the blue line, wind energy growth in Alberta. And you can see in the last few years, wind energy is really starting to pick up with the potential projects, with the proposed and the advanced development, like skyrocketing, almost more than doubling the installed capacity. But there's a few obstacles, and there's a good chance that not all of these proposed or advanced development projects will actually be built. So we're going to talk about one of these obstacles, which is the wind discount that I kind of mentioned earlier. But to understand wind discount, we have to kind of understand how Alberta's electricity market works. So in the market, suppliers enter offers for their power or their energy, and these offers are sorted in what's called a merit order from low to high. So this illustration on this slide helps show a little bit of how that works, with each column kind of representing one of the suppliers with their offer. And the energy is dispatched, starting with the low offers to ensure the lowest cost for the consumers, and working its way up the merit order until that electricity demand is met. And that last offer that satisfies the electricity demand sets what's called the system marginal price, or the SMP. And the average of the time-weighted SMPs sets the pool price. And the pool price is the revenue that the suppliers receive for their money. So as you can see in this chart, the more low-cost resources that we have in the market, the lower the price. And with that in mind, wind energy offers into this market at $0, as there's a zero fuel cost. And this also ensures that all available wind energy is dispatched. But that also results that on average, wind energy receives lower prices for their energy that they produce in Alberta. So you can see with this chart here, with the black line representing the market average prices that are received by suppliers, and the green representing wind energy prices that are captured on average. And over the last 11 years, it has consistently been less than the market average. So this phenomenon, or these lower prices, are known as wind discount. So what causes wind discount? Well, there's a few things, but the main one I kind of want to focus on is the dramatic swings in energy output. So you can see in this chart where the red line kind of shows the pool price over this week span from last year, and the black line shows wind energy output. And you can see there are dramatic swings where it's ranging from almost 900 megawatts down, or megawatt hours, down to zero many times throughout the week. And a lot of that influences the price, because we kind of talked about it earlier, but as the supply of energy increases and the demand remains constant, the price drops, resulting in lower prices for that electricity. So there's a few things that affect why there's such dramatic swings in energy output. And one of them has to do with where these wind farms are located. So as you can see in this map, which is drawn from the Canada Wind Atlas, it shows wind speeds from 80 meters above the ground, that historically a lot of the wind farms in Alberta have been built in the southwestern portion of the province, kind of near Pincher Creek. And you can see that circled on the left map there with the black dot showing active wind farms. And the problem with this is when the wind blows, they all come online together, which causes the dramatic increase. But then when the wind stops, they all come offline at the same time. And thus we have these dramatic swings and an accented wind discount. So what some of the newer projects or proposed projects are trying to do is they're trying to spread out across the province. And you can see that on the right-hand side, where projects in the ASOQ are marked with the gray diamonds, and they're spread out over a larger portion of the province. And although they might not be capturing the same wind resources that some of the current active farms are capturing, their hope is that they can capture the wind resource at times that don't correlate with the rest of the fleet. And therefore they can hopefully capture higher prices. And so our research is to try to take this a step further. So you can see in this map, we've identified a few locations already with the red triangles here, where we're trying to identify locations that have a decent wind profile and that are relatively close to some existing power lines. And we're trying to generate wind profiles for these locations. And once we've generated a wind profile for these locations, we are simulating Alberta's electricity market with these resources available. And we're going to try to determine which resources, if any of these, are economical to build. And then finally, we have to verify the results of our simulation against actual data to make sure we've built a model that reflects Alberta's economy. So for the wind profile portion, we're building off methodology that has been developed by University of Alberta alum Natalia Bonilla. And this methodology simulates the energy generated by hypothetical wind farms, so perfect for this research. And it draws data from the Canada Wind Atlas numerical weather prediction model, and it uses a generic loss coefficient to estimate wind energy at given locations. And so we're trying to adapt this to be able to fit a wind profile that we can enter into our model that we're creating. And so we're creating this model using Energy Exemplar's Aurora software. And this software allows us to input different resources. We've input a lot of the resources in the ASOQ, as well as some of these hypothetical wind farm locations that we've created. And the software uses an iterative process to determine when to build new resources and which resources are economical to build. So on the right here, you can see a sample simulation that we've done, where the top chart shows resources that a simulation wanted to build. And the bottom chart shows resources that were available to the simulation to build, but chose not to build. And out of these, you can see that the simulation really wanted to build a lot at 3 locations in particular. And 2 of those locations marked in green are some of our hypothetical wind farm locations. So at least this model and this simulation are supporting this concept and validating our theory. But we have to verify that this model and the simulation are accurate. Otherwise, this isn't really helpful. So we started to try to plot these side by side. So you can see on the left-hand side, we have our simulated data. And on the right-hand side, we have actual ASO data for the same time period. And this particular week section is from March of 2020. And as you can see, the black thick line on the bottom graph shows the demand. And that one actually follows a fairly similar curve in both instances. So our demand is fairly similar with our simulation, with the resources following similar trends with some tweaking and some alterations that need to happen. But our biggest concern that we're trying to address right now is that pool price. Because as you can see, the pool price looks very dissimilar to the ASO actual data for that time. And so we're trying to develop this model, trying to identify variables and ways that we can better predict how Alberta's electricity market is going to be moving forward so that we can have a higher accuracy with our model. So with all of that in mind, if we can get this model to be accurate, if we can make sure that we have the results that we're hoping for and that they can accurately reflect the future, we're hoping that we can optimize the wind energy fleet and that this can lead to lower costs both for consumers and suppliers. And a lot of that will be because of the reliability and supply that will be of wind energy that increases. So by increasing the reliability and supply, consumers can see lower costs because there's less spikes in the prices that you see. There's a more consistent stream of wind energy. And this consistent stream also lowers costs for suppliers because they have a more consistent supply of revenue, and the wind discount isn't quite as accented for a lot of these locations. And as well, by diversifying the locations, we're also able to diversify the fleet impact on an area. So I was raised in southern Alberta, kind of near Pincher Creek, where a lot of these wind farms are. And for anyone who has visited the region, you can attest that you can see wind turbines almost everywhere. And while a lot of people like myself are quite excited by that prospect, there's a public image and a concern that it can negatively affect and impact the environment around us. And so by diversifying the fleet and lowering the concentration in areas, we can hopefully increase that public image and decrease the effect on any particular area. And by doing so, we can get the most out of some of these resources so that we don't have to overbuild our wind resource to be able to meet the demand and have a higher market saturation. So thank you for your time, and I hope this has been helpful for you. Are there any questions?
Thanks, Taylor. I'm not seeing any burning follow-up questions. I've got a quick question I want to ask. Maybe I'll just, obviously I'm working with Taylor on this work. One thing I should maybe throw in as a very quick clarification, if you were looking at the data between ISO and our simulation, that the Alberta, as I said right at the beginning of this this session, that the system is sort of unfolding quickly before our eyes, and so plants are being, some of them are changing fuels or retiring sort of in real time, and so that makes modeling the system a bit tricky because it's not as static as many electricity systems are these days. It's a lot of change going on. So thanks for that, Taylor. Oh, we do have a question in here quick. So maybe we'll do one follow-up here quick, and then I'll save a couple of these for afterwards. But maybe the one question, Taylor, maybe just a quick one you can maybe answer right away is energy storage and where that is that included in the model at this stage in the game?
Yeah, so we're trying to build energy storage into our model. It's something we're still developing, but we are trying to input resources and develop, like our simulations right now are using a mixed integer program to try to simulate and try to determine when the best times to use storage are. But currently our results aren't wanting to build a lot of storage because, as you can see from our price, we don't have a lot of price volatility, which means that there's not a lot of benefit to having storage. So we're hoping by better modeling the price volatility that will encourage the simulation to build more storage in the future. I hope that answered your question.
Thanks, Taylor. There's a couple more questions, but maybe I'll save them for the broader plenary there, and we'll move it on to our final presentation. So thanks for that, Taylor. And our final presenter talking about, so shifting gears here a little bit and talk about curriculum development. I'm excited to have this as part of the conversation. Many of my students are asking about how did they get into renewables, and why does our sort of current engineering curriculum not include emphasis on renewables? So great to see this being discussed. So I'll hand it over to Lindsay Miller from University of Windsor to carry on with our final presentation here. So welcome, Lindsay.
Thanks, Tim. And Marianne, I'll have you share our slides if that's okay as well. Sorry. Okay.
Are you able to share the slides, Marianne? Or yeah, okay. Perfect.
Okay, so while they're coming up, I'll just say we're happy to be here. So I think we're the only presentation in the curriculum development section, but that's okay. We have a couple things to report on a sort of ongoing project that we're sort of in the middle of. So our title here is Improved Wind Energy Curriculum to Support Canada's Transitioning Energy Sector. It's a little bit more than just wind. We're talking a little bit more about renewables at large, but we'll get to that. So next slide, please. So the project is actually funded by Sustainable Development Goals Fund project, and that's initiated through Economic and Social Development Canada. So the title of our broader project is Diverse and Dynamic Curriculum to Support Canada's Clean Energy Transition, and that's what we'll be talking about today. Next slide. So just a bit of an overview to start. Our sort of problem statement, so to speak, is that you probably, our energy systems are undergoing unprecedented spectrums of changes right now. What we believe here is that the same cannot be said for the conventional educational pathways that were designed to produce the highly qualified people to drive the energy sector. So there's so much changing in our energy sector, both in renewables and in non-renewables, and in the integration and in storage, but our curriculum isn't keeping up. That's sort of our problem statement, at least, which we based our project on. So myself and Dr. Caraveau and the other people that we work with here at the Environmental Energy Institute and the Turbulence and Energy Lab, we work quite a bit with industry professionals and stakeholders, many of whom are on the call today as well. So just through preliminary discussions and with the projects that we've been involved in with them, our industry stakeholders are suggesting that the sector could benefit from flexible HQP, that's our highly qualified people, that have a broad knowledge of technical, economic, and policy connected approach to equip Canada with a culturally gender diverse and inclusive pool of HQP who can bridge the gaps between the technical, economic, and social aspects of the clean energy sector. So what we're really saying here is that, we do have some people that might have an electrical engineering degree, or you might have some people that have, a bit of technical or economic knowledge, but really to have these HQP that have knowledge of all three of these aspects and are able to really take the sector to where it needs to go, we're finding there's a real gap there. So just real quick here with our infographic, I'm not going to go through it all, but a couple of things to point out. Of the 280 post-secondary institutions in Canada, only 12 of them offer programs in clean energy. So that's only about 4%, right? So when we think about how much the sector drives so much of what we do, it's really important, I think, for us to address that and try to understand how we can get more programs offering clean energy options, and also co-op and internship opportunities, which we think are really important to developing our HQP properly. Next slide. So the overarching objectives are to inform clean energy curriculum development and also encourage women to pursue clean energy careers to ultimately advance Canada's preparedness for continued transition to a clean energy economy. So we had to sort of build this project around some of the sustainable development goals. So some of the ones we selected were clean energy for all, advancing equity, and improved curriculum. So we had to pick 3 SDGs. So we sort of combined those into our project objectives here. And our approach is to really try to increase our engagement. So engage a broad and diverse cross-section of energy sector stakeholders to really gain perspective on the skill sets and experience that will support this transition. So we don't think we're going to get too far talking to other academics, although we've included them in our discussion. We're really trying to engage with the people who are looking to hire people in the future and understand what they want of our HQP coming out of our institutions, and how we can best prepare people to be useful in that sector. So the insights that we've collected will be used to inform our post-secondary institutions on how we can better prepare HQP that will be entering the sector upon graduation. Next slide. So just where are we at? So we had a kickoff meeting last summer in Toronto where we just had a small group gather to discuss how to sort of best go forward with this. We had 3 workshops so far, which I think is pretty exciting achievement considering we've been trying to do this throughout COVID, but we did have one in Ottawa where we had a workshop and we had some survey questions and some presentations from some of our graduate students. We had a second smaller meeting and workshop in Prince Edward Island where we did meet with our friends here from the Wind Energy Institute of Canada and also with Maritime Electric to get some information on what they were looking for in their future hires as well and sort of how they thought the sector was doing right now in terms of their preparation. And then recently we had a workshop in Vancouver and Victoria as well. So we really tried to get across the country here and get some broad insights. In addition to those, we've had some electronic surveys go out, so maybe some of you have participated as well, and just asking those same questions of, what do we expect from our HQP? What can we do to better prepare them? We've been asking questions like, is it really a new program? Is it a new course? Should it be micro-credentials? Do you think the majority of the training should be happening actually when they get to the workplace anyways? And, our job really is just to produce the electrical engineer or someone similar. At the same time as we've been doing those engagement activities, we've had some of our graduate students working to develop a landscape of what we've called a landscape of clean energy curriculum in Canada. So where are the programs being offered? What are they offering? Is there co-op? Is it more holistic or is it just really specific to a specific energy sector? And then also at the same time, looking at the clean energy employment opportunity projections. So where are the jobs going to be? And then trying to focus our, preparing our HQP for those specific opportunities that are going to come in the future. Next slide. So our engagement activities have focused on gaining insight into the technical and professional skills and experience that stakeholders anticipate will be required of the future HQP entering the sector, like I mentioned, the specific roles women are gravitating towards, and the gaps between the skill sets we've identified and the current Canadian post-secondary clean energy curriculum. Next slide. So this is I just have 2 slides here that sort of look at the landscape that I mentioned that our graduate students were looking at. So I won't go through it in great detail. I only have a minute or 2 left here, but just trying to look at what is available, right? So we found there's about 6 certificate programs, 2 diploma programs, 4 undergraduate, 4 masters, and 3 continuing education programs. And where are those located? One at USask, Saskatchewan that has a master's program, one at UBC, one in Dalhousie, 2 at U of T. So we can kind of see where these programs are. And we also went through to kind of look at what courses were offered, which ones offered co-op, which ones offered internship, which ones combine the technical skills with the policy related aspects, et cetera. But I won't go into all of that. So next slide. And then, like I mentioned, at the same time, we're trying to see where are the clean energy jobs. So we've noted some of the statistics that we can easily look up, but there'll be about 639,000 jobs in Canada's clean energy sector in 2023, which is up considerably from, in 2030, which is up considerably from 2020. They're set to grow about 50%, while fossil fuels are on track to drop, right? Just given the differences in how the sector is going to be moving. And the fastest growing clean energy industry is in EV technology. And another industry expected to take off is hydrogen technology. So just kind of keeping track of where we're expecting the jobs to be so that we can make sure we're properly preparing our HQP to be ready to assist the sector in moving forward. And I think I just have one more slide. All right, so we just basically want to take these 5 minutes today to make you guys aware of the work that we're doing. We're also working with NAWER, the North American Wind Energy Academy on some work there and offering some courses through their WindU, I think they call it. So we're trying to get just more people involved, right? So we are still trying to engage additional stakeholders. The project is still ongoing. So if you have anything you'd like to add, please reach out to us. We are still trying to determine the best way forward, right? So this project is really about developing recommendations. So again, should we have a whole new program? Should we have new courses? Are micro-credentials better? Is it best just to have the work done on site when people get to the specific job because it's too specific to actually make a broad course of it? We're trying to develop those recommendations and then develop mechanisms for continued stakeholder engagement. So we don't want this to end with this project. We want our industry stakeholders to be able to continuously sort of inform curriculum development so that, we are best preparing the HQP to help with the sector and then ultimately get to the development of the new curriculum if we find that's the best way going forward. So just wanted to get that out there so, everyone knows we're working on it, and we'd love to hear from anybody who wants to stay engaged with us. So that's all I have.
That's great. Thank you so much. I'm personally really glad to hear that. As I said, it's the #1 question I get from my graduating 4th year engineering students, which is interesting coming out of Alberta, that there definitely, I feel like there's a anecdotal, obviously, but a transition in terms of what engineers are thinking their future careers might look like in the energy sector. I see a question from Andrea Krajdev. If you want to ask a question.
Yeah, hi, Tim. Hi, thanks, Lindsay. So I'm wondering who at USask you're in contact with about the master's program.
So I actually have to defer to our graduate student, Agatha. I'm not sure she was in contact with anybody or was just trying to develop that map of where the programs are being offered. So she's the one that prepared those couple slides for us on the landscape of the programs there.
The reason I reach out is because I'm probably that person. So okay. I've been developing the curriculum program for, it's called Masters of Sustainability and Energy Security. And it's probably that one. Yeah, so I've been working on that, and I've developed 3 courses in renewable energy related to that. And just a little note on that program, it's really an interdisciplinary program. The first year is it's a 2-year part-time program with working professionals, and we've had a range of different students. It's primarily targeted at Indigenous populations, Indigenous students. We've had in the first cohort, 60% were women, 50% Indigenous, and 1 engineer. The rest are primarily a mix between policy, arts, and other areas. So it's a really, I wouldn't say it's a very technically heavy course in terms of it, but it does bring in the different aspects of developing renewable energy projects in remote communities. So
that's great. And if you don't mind, we'll follow up with you, because I don't think Agatha had actually reached out to anybody. She was just trying to develop a map of what was out there right now, but it'd be 100%. Good to reach out in the future for sure. Thanks, Andrea.
You're welcome.
Hi, Lindsay. This is Mariano from Mohawk College. Actually, my point was more about colleges. It seems that they're targeting their universities, but there's a lot of skills there that at the college level can be part of these micro-credentials. Is there any topics that are going to be met like that universities, colleges can work together?
Yeah, for sure. We've been in touch with some colleges as well. I'm not sure we included those on our slides, but we have been in touch with them as well. And we're trying to collaborate with our local college as well. I feel like we acknowledge that the colleges are sometimes quite a bit more nimble and able to pick up on the transition skills and get those out there quicker than the university. So it's a good asset for us to keep in touch with the colleges as well.
Perfect. Yeah, I can follow up with you regarding that.
Yeah, that would be great.
Perfect. Well, glad to hear that we're making connections already. That was obviously part of the purpose of today.
For sure.
So,
thanks, Tim.
Great. Thanks so much for that. I guess so now we don't have that much time left, but if we have moment sort of for broader questions for any of the panelists that we've heard from, now would be the time to ask them. I've collected a few from either the chat or even potentially a couple of my own from along the way. So maybe because I have the mic, I'll ask my own first. This goes back to our first presenter there about the tomatoes and wind turbines there. I'm just curious what the remaining lifetimes expected on some of those wind farms, sort of post feed-in tariff contracts or LRP contracts, as the case may be. Also, I don't know if you're in touch at all with the Business Renewables Center. I think they've largely been focused in Alberta, but they've been working. There's been a lot of active contracts between PPAs being signed in Alberta these days, direct PPAs between wind farms and private off-takers. I don't know if that's something that might be useful in the Ontario context or not. So I don't know if you've been in touch with them. I don't know if we still have with us. Maybe I should have checked that before I asked the question. Perhaps not. So maybe I'll follow up with him then offline. Taylor, there was a couple of questions for you about the model that you'd presented in Alberta. One about sort of what were some of the key inputs into it, and another one about does as an increasing sort of geographically diverse fleet may arise in Alberta, does that also have a corresponding increase in capacity factors. Maybe I'll let you try to take on both of those.
Yeah, for sure. So first for the input. So the nice thing about this particular software and Energy Exemplar is they actually have some base databases that they provide with the software for various regions. And Alberta happens to be one of those regions. We found that there's obviously a lot that's still out of date and stuff. So we've had to go through and try to update the input database and try to find where we can find discrepancies, what we can change. But yeah, the base database actually comes from the software, and then we're trying to fill in the gaps or change as needed. And to follow up with the second question about the capacity factor. As we're diversifying the fleet, there's actually a very good chance that the overall capacity factor could actually decrease because we have a higher installed capacity that's spread over lesser resource, if that makes sense. So that resource might not produce as much energy, but it's able to capture higher prices. And so that's the thing to catch in there. I don't know if that answers your questions.
Yes, thank you.
Thanks, Taylor. Maybe I'll just throw in one other quick thing. Obviously, some of the really key inputs that go into the model, especially these days in Alberta, is future gas prices and heat rates for new and upcoming plants. So, but basically every individual power plant's performance and economics are individually modeled in the software. Another question came in here this one's for Lindsay, I guess, about connecting with folks in Europe. Is that part of the program that you're developing as well, or is that taken into consideration? Are you still with us, Lindsay?
I don't see Lindsay here.
Oh, maybe that's another one we'll follow up with with offline. I had one other question, maybe for Eldrick or perhaps Sophia, but looking at sort of a different product. There's obviously the technical side of looking at the product, ride through capacity, or whatever your frequency response, I guess I should say. That's not traditionally the way wind farms have been contracted. Obviously, for the most part, at least IPPs are typically only selling their energy. How far along are we in terms of actually compensating companies for maybe operating in a slightly different? What's the state of the development in terms of a financial reward for some of these non-energy components of their generation? I don't know if I can hear you there, Eldrick.
Still nothing?
Oh, I can hear you now. Perfect.
Okay, perfect. I can try and answer that question to some extent. One of the challenges with these, with some ancillary services, is that historically it's kind of been seen as a given. So it's there. There wasn't really a requirement to get them from somewhere else. One of the things we tested with Enercon and Nova Scotia Power was fast frequency response. That's kind of mimicking inertial response from a synchronous machine. But the difference is a synchronous machine just does that. There's nothing you have to do to get that response from a synchronous machine. That's not the case with power electronics and a wind turbine. So I think there will be an inflection point soon. I don't know how soon, but somewhere where, depending on where you are in the country, the amount of energy that you're getting from wind or any inverter surpasses the amount coming from synchronous machines. That may be the point where the value of the service will have to be calculated. Now that's one side of the spectrum. The other is something like AGC. So that's historically been done from a variety of generators, and that's primarily been driven by fuel cost. Of course, given the fact that Canada has a lot of hydro and nuclear, there isn't really a lot of pressure on price. But that's not the case in places like Ireland or Australia even, where backup generation or synchronous generation tends to have a significant fuel cost. So those are places that we tend to look to for pointers as how do you value these things? How do you price them out? How do you pay a generator for this? But overall, I tend to agree with what you said initially, that these renewable generators tend to be seen as just sources of energy only. It hasn't really changed much, but we do have a report out that attempts an answer. So depending on where you are in the country, different amounts of progress have been made.
Yeah, can I add something to that? When I was doing my research and we're talking with the ISO, we found out that probably not most of the programs, but at least some of them, specifically those that provide frequency regulation, they are trying to be technology agnostic, which could be a really good thing for like these renewable resources, right? Because if they are able to provide different service and the provision of frequency regulation is going to be paid off just based on the service that they are provide, without seeing if this is a battery, if this is a wind turbine, if this is a flywheel or any other type of technology. That's a really good way to address this. They are remain or try to stay blind of what type of technology it's used, as long as it's doing the job they are kind of being contracted to do. So
Great, thanks for that. Do we have any other questions from the audience at this stage in the game? The presentations were thorough enough that all the questions got answered. Well, I'll give you another 5 seconds to think about a question, but otherwise, I think we're pretty close to the end of our allotted time, as it were. Anyway, so if there's nothing else burning that's coming in, obviously, if you missed something, this was being recorded, and I think we'll make it available to folks if you want to sort of follow up with anything that was presented here today. So I guess I'll wrap it up then. Thanks so much for everyone's participation. Thanks for our presenters. This was a super interesting way to spend the day, and it was really nice to see what's going on. And I look forward to the remaining 3 or 4 sessions that we have. So Marianne, I don't know if you have anything you want to add to close it off, but appreciate everyone putting this together.
Thank you all. Thank you, Tim, and all the presenters. This was another great session. And join us on Friday for cold climate and forecasting for our next in the webinar series.
Great. Thanks so much, everyone.
Thanks, everyone. Thanks, Tim.
thank you.